Hello and welcome back. In the last video, this is where we left off. We have some device information on the screen, some malloc addresses, and some Gs being printed using a sleep function. In this video, we're going to be implementing an Ahci driver so that we can read from disks and optical drives. Let's get started. Alright, so the first thing I wanted to do is just clean up our start function so we can get rid of everything except for the kernel info equals initialize kernel and the while true loop. And just to increase the CPU power efficiency while running the operating system, we just need to do ASM halt. So this will pause the CPU when it's not doing anything, and it will resume whenever it receives an interrupt. Right, the next thing I wanted to do is do a quick few bug fixes. The first of which is in heap.cpp inside of the combine forward function. We need to make it so the next segment equals the next segment's next segment. If we don't do this, then the future segments after these segments have been combined won't link up to each other correctly. So we just need to put that line in there before the last line of the function. The next one I want to fix actually dates back pretty early in the series, and this is inside of the bitmap.cpp file. There's a problem with this subscript operator, and I can't really pinpoint what it is, but if we change this to a getter instead of the subscript operator, it fixes the problem. So we can just copy that, paste it, and change the operator subscript to a get. And then inside of the operator subscript, we can call that get function. So get index. And then inside bitmap.h, we need to declare that function. So get uint64t index. Now we can clean our project by deleting the lib folder and then build and run everything, and then everything should just be working as it was before. These bugs were just running around in the background, not causing any mischief, but if you dig deeper and try to do something a little bit more complicated, then they do pop their ugly heads up. So as you can see, we just have our device information displayed on the screen. Now, let's move on to creating an Ahci driver. So now the first step we need to take is actually creating some source files for the Ahci driver. So let's create a new folder, call it Ahci, and inside of that folder, create ahci.h. Then we can do pragma once, include standard int.h, and we can put everything inside the Ahci driver code inside of a namespace named Ahci. Now, since we're using C++, we may as well use a class for this. If you're using C or some other language that doesn't support classes, then a struct will work just fine. And we want to create a class Ahci Driver. And we're going to expand this eventually, but we need to start off with the constructor, destructor, and then a member to store the PCI base address. So let's do that. Ahci Driver. And this needs to take a pointer to our PCI base address. So we need to include //PCI.h so that we can access the PCI : PCI device header pointer PCI base address. Right, now we need our destructor, which is just squiggly line Ahci driver brackets, and then we need a variable to store the PCI base address. So PCI device header pointer PCI base address, and we'll make this just capital PCI base address. Right, now that we have that, we can create our CPP file. So ahci.cpp, and within that file we include ahci.h and also add in our Ahci namespace. Now we need to create our constructor and destructor. So Ahci driver : Ahci driver, and the PCI : PCI device header pointer PCI base address as our parameter, and then this PCI base address equals PCI base address. Right. Now we need to create the destructor, so Ahci driver : squiggly line Ahci driver. And we don't do anything at the moment because we don't have any dynamically allocated memory to clean up. Right, now that we have that, we can do a little test to see if our Ahci driver instance has been initialized properly. So we can include /basic renderer.h, and then we can do global renderer.print Ahci driver instance initialized. And now we can do global renderer next, just to make sure it's all spaced out correctly. Now we need to also make sure that we have support for the new and delete operators in our heap. So this is pretty simple to add. So let's add that now. It's just a couple of lines in our header. So we have an inline void pointer operator new, taking a size t size, and this returns malloc size. Then we also need to make a copy of that for the array to make a new array. Then we need the inline void operator delete void pointer p for pointer, and then we just free p. That's how you create the new and delete operators. Now there's one more thing. We need to make sure that exceptions are disabled in our project, or else using new and delete will cause a problem. So in our makefile, we need to add a new flag, f node-exceptions. We need to disable exceptions in C++ because that depends on external dependencies, which we don't have. Now that we have those, we can go on and identify our Ahci device in our PCI function and create an instance of our driver. So inside of the enumerate function, inside of the PCI source file, we can identify our Ahci device and create the driver. So switch PCI device header class, and in the case that it is 0x01, which is a mass storage controller, we can now switch in the PCI device header subclass, and in the case that it is 0x06, meaning it is serial ATA for SATA, we can then switch the PCI device headers program interface, and on the case that it is 0x01, we have identified our Ahci 1.0 device, and we can create a driver for it. So Ahci, well, we need to include Ahci, so at the top just include Ahci /Ahci. So now we can do new Ahci : Ahci driver PCI device header. Alright, now it's telling us that this constructor is inaccessible. That's because we need to declare it ill as public using the public keyword in the class. Right. Now when we run that, it should call this constructor because we're using the new operator, and then it should print to the screen Ahci driver instance initialized. So let's test and see if it works. Alright, so we have an undefined reference to operator new, and that's because we didn't include heap.h. So include memory /heap.h. Now we need to clean the project again, so just delete the lib folder or use your clean make routine if you've created one. So we run that, and there we go. It's all linked properly, and if everything works properly, we should have that text displayed on the screen. Alright, so as you can see, Ahci driver instance initialized, which means we now have an Ahci driver that knows about the memory mapped location of this Ahci device. Now we can program the driver to do whatever it wants with the device, because that's how we've done it. Now let's get on to setting up some important stuff about Ahci. Alright, so now we need to create two Ahci structs. The first one being the host bus adapter port, which is HBA port, and the second one being the host bus adapter memory, so HBA memory. Inside the host bus adapter memory, we have quite a few members. We have uint32t host capability. If you'd like to know more about what these members are and what they do, the link to the Ahci specification will be in the description. I won't go into it here because it's far too much to cover in 1 or 2 videos, but I will try and cover the bits that we will be using in our driver. But for now, we're just copying out the values for these structs. The second one is the global host control. Then we have interrupt status. If you don't want to write all these out by hand, you can just go to the project's GitHub, which is also in a link in the description, and copy these out as we go. Right, then we have the ports implemented, UN32T version, UN32T CCC control, UN32T CCC ports, UN32T enclosure management location, UN32T enclosure management control, UN32T host capabilities extended, UN32T BIOS handoff control and status. Now we have 74 reserved bytes, so reserved 0x74, so it wasn't 74, it was 74 hexadecimal. Then we have 60 vendor specific bytes, so uint8t vendor 0x60. Then we have the host bus adapter port, so HBA port, ports, and we can just make this an array of size 1. Now that we have that, we need to fill out the HBA port struct. This one's a little bit longer, but we can just power our way through it. uint32t command list base, uint32t command list base upper. These two 32-bit values combine into one 64-bit value, but it is listed in the specification as two 32-bit values, and I don't like combining them because with memory mapped I/O you never know what could happen, so it's best just to run by the specification. Then we have UN32T FIS base address, UN32T FIS base address upper, UN32T interrupt status, UN32T interrupt enable, UN32T command and status, UN32T reserved 0, UN32T task file data, UN32T signature, UN32T SATA status, UN32T SATA control, UN32T SATA error, UN32T SATA active, UN32T command issue, UN32T SATA notification, UN32T FIS switch control, UN32T reserved 1, and this is 11 32-bit values have been reserved. Then we have a 4 size array for vendor data. So we have 4 32-bit values at the end. Now that we have those structs, we can store a pointer to the HBA memory of this Ahci device. So we can do HBA memory pointer A bar. And we actually need another type of PCI device header before we can do that. So we'll go back into our PCI namespace and we'll declare our new PCI device header. And this header just expands upon this first PCI device header. It actually contains this header as the header for the new header. It just adds some more data that we can play with. So struct PCI header 0. There's quite a few headers that we can make here. So that's why I'm calling it 0. It takes the PCI device header. Alright, then we have a uint32t bar 0, uint32t bar 1. These are the base address registers, by the way. We need those for quite a lot of PCI devices. uint32 bar 2, uint32 bar 3, uint32 bar 4, uint32 bar 5. So we've got 6 base address registers in total. Then we have a uint32 card bus CIS pointer. Then a uint16 subsystem vendor ID. Then uint16t subsystem ID. uint32t expansion ROM base address, uint8 capabilities pointer, uint8 reserved 0, uint16 reserved 1, uint32 reserved 2 uint8 interrupt line uint8 interrupt pin uint8 minimum grant and uint8 maximum latency. Alright, I recommend just checking through that to make sure it is all exactly the same. I also recommend checking it against the GitHub repo to make sure there's no discrepancies. Right, now we can head back into ahci.cpp and we can set our a bar. A bar equals casted to a PCI : PCI header 0 pointer, PCI base address. And the base address that we are looking for is located at bar 5. And we're going to need to cast this to our host bus adapter memory pointer. So HBA memory. The next thing we need to do is map the A bar, the Ahci base address register, to itself. So we need access to our page table manager. So include .. /paging / page table manager. Then we can do g page table manager .map memory a bar. Right, now that we've mapped that memory, next thing we need to do is set up all of the ports with the required data. Alright, so now we need to make a way to probe the ports of the Ahci device to see which ports are active and in use. So let's create a new function in our Ahci Driver class. Let's call it void probe ports, and in ahci.cpp we can now implement that function. So Ahci Driver : probe ports, and put a void at the start to signify that it's a function that returns nothing. Alright, so there is a possible maximum 32 ports that we can access, and if a port is active, then we are able to check it in a ports implemented bit mask. So we can store the value ports implemented equals a bar ports implemented. And then we can do a for int I equals 0, I less than 32, I plus plus. So we iterate through all 32 possible ports. And then we can do if ports implemented and 1 bit shifted to the left by I, then the port is active. And then we can check what type of port it is. So before we can do that, we need to actually create some enums about what ports could exist. So in ahci.h, we can create our enum port type, and there is 5 different port types we can use. The first is none. So none equals 0, SATA equals 1, SEMB equals 2, PM equals 3, and SATA PI equals 4. The only ones we're going to be worrying about is none, SATA, and SATA PI. The other two do have their uses, but we won't be covering them in this video. SATA is your normal drives such as hard drives, and SATA PI are drives such as optical drives. Alright, now I need to create a function to check the specific port and figure out what type it is. So we can create a function, port type, check port type, and we can take a pointer to the host bus adapter port pointer port. So we need to store a uint32 SATA status equals the port's SATA status. Now we need to store some information about the interface's power management. So uint8t interface power management equals SATA status bit shifted to the right and 0B111. So as we look here in the Ahci specification, in the port serial status register, we have the interface power management bit field, and it is 3 bits starting at the 8th bit. And we need to check if the port is in the active state, so 1H. But we'll do that in a second. We'll just store another value, and this value is the device detection value, and this one is uint8 device detection equals SATA status and 0B111, as this one is also 3 bits. Alright, now we can check if device detection does not equal present, so if it is not detected and physical communication established, which is a value of 3, so 0x03 or 0x3. If device detection is not 0x3, we can actually create a define for this to keep it nice and clean. HBA underscore port underscore device underscore present 0x3. So we can check if it is not that value. We can return port type none. Then we can check if the interface power management is what we need it to be. So if interface power management does not equal, and the value we need it to be is 1, so we can create another define for that. Define HBA underscore port underscore IPM underscore active 0x1. So if it does not equal that value, we can then return port type none. Right, now we need to check the signature of the port to find out which sort of port it is. So switch port signature, and we can create a few more defines. So the first one is define SATA signature ATAPI, and this is a value of 0xEB140101. The next one we need to do is the signature for ATA, so define SATA underscore signature underscore ATA, and this is a value of 00000101. The next one is SATA underscore signature underscore SEMB, and this is a value of 0xC33C0101. And the last one we need to do is SATA underscore signature underscore PM. This is 0x96690101. So now we can check against all of these values and return the corresponding enum. So in the case that it is SATA underscore signature underscore ATAPI, we can return port type SATA PI. In the case that it is SATA signature ATA, we return port type SATA. In the case that it is signature PM, we return port type PM. And in the case that it is SEMB, we return port type SEMB. And on the default case, which means if it is none of the above, we return port type none. Now back in our probe ports function, we can get the port type of our port by doing port type equals check port type. And then we need to pass in the pointer to our port so we can get the address of our A bar ports array indexed by I. And just for testing, we can do like if port type equals port type SATA global renderer.print SATA drive global renderer.next. Then else, we can just copy all of that. If it is SATA PI, we can return SATA PI drive. Else, we can just return not interested, because the only drives we're looking for right now is either SATA or SATA PI. Right, now that we have that probe ports function, we can call it from within our Ahci driver and test that and see what happens. Alright, so as you can see, we have a SATA drive, we have another not interested, we have a SATA PI drive, and then 3 not interested. So we have 1 hard drive and 1 optical drive that QEMU is providing for us. So we can add 1 more drive just to see how QEMU reacts and see how our operating system reacts. So if we go into, so we can just go to our bin folder, reveal in Explorer, and create a new file that we can pass into a new drive. So let's just call it blank.img. And then using that, we can pass it in as another drive using our build directory /blank.img. Then we can run that and see if we have another SATA drive in our operating system. Alright, so now as you can see we have 2 SATA drives and 1 SATA PI drive, so adding another drive to our operating system has been successfully detected. Alright, that will be it for this video. In the next video we will go into setting up some commands to send to the ports and seeing if we can get a read from one of the drives. Alright, thank you for watching and I will see you next time. Alright, I just wanted to say thank you to my tier 2 patrons, Bobby Addison, Coffee Pot, Cole Fodorado, Daniel Cosper, Daniel Solov, Dual Chem, Jim Borden, John M, Kevin++, Mad Max++, Michael Bush, Michael W. Atkinson, Sun C, and to my tier 1 patrons, David Gonzalez, Kenneth Looney, and THXTNT the Gamer. I appreciate all the support you can give, you are all awesome.